Hi, my name is Alex Stafford and I'm a physics tutor at the Peer Tutoring Lab for the Student Success Centre. And today we are going to be doing the first in a two-series video about momentum. And so today we'll be covering elastic collisions. So to introduce elastic collisions, we first have to introduce what momentum is. And so as an informal definition, we could say it is a concept that allows us to predict the effects of collisions on certain objects. And so formally we define momentum as P, and it's equal to the product of mass and velocity. And because velocity is a vector, momentum will also be a vector. And so it has units of kilograms meters per second. And so something really useful about momentum that we can use in these collisions is the conservation law. So for no external forces, the total momentum is conserved within a system. And so that would mean your P initial is equal to your P final. So for example, if we have two objects colliding in 1D, they collide here, and then they go their separate ways. This has M1 and this has M2, and initially they have each of different velocities. Obviously, finally they're going to have different velocities, so label that V1F and V2F. So for this collision, Pi is equal to Pf, which means M1 V1 initial plus M2 V2 initial. The total momentum initially is equal to the total momentum finally. So that's M1 V1F plus M2 V2F. And so this is very useful when figuring out the velocities after collisions or the velocities before collisions. And so this is a specific example for this problem that I just had here, but this Pi is equal to Pf is valid for any system where there are no external forces. And so now we can ask, what are elastic collisions? Well, an elastic collision is one where objects bounce off each other, i.e. there is little to no friction. And so we can see that this example that we have here is an elastic collision as they bounce off each other. And so we have another definition, which is perfectly elastic collisions, which means the kinetic energy of the system is conserved as well. So when we have a perfectly elastic collision, we have both momentum and kinetic energy being conserved. And so for this example that we have here, this is going to be 1/2 M1 V1F squared. Sorry, that's initially. Plus 1/2 M2 V2 initial squared. So the initial kinetic energy of both our balls is equal to 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. So for perfectly elastic collisions, we have two equations that can model our motion. The momentum, the conservation of momentum, and the conservation of energy. So let's do an example problem. In this problem, we have a billiard ball of a certain mass going in a certain direction with initial velocity, colliding with another billiard ball that's slightly smaller, going with a faster velocity. And the question is, what is the change in kinetic energy of billet ball 1? And they stipulate for us that it is a perfectly elastic collision, which is good, which means we can use two sets of equations for this problem. And so you might be tempted to say that energy is conserved for perfectly elastic, which means ball 1 doesn't lose any energy, right? Well, that's wrong. Remember from our previous example, kinetic energy of the system is conserved, not specific objects within the system. And so billet ball 1 and 2, their energy combined will stay the same. There might be some transfer of energy between the two billet balls, so we can't say that. And so because we know it's a perfectly elastic collision, we know there are two conserved quantities: momentum and kinetic energy. And so let's set up our equations. So conservation of momentum equation. Pi is equal to Pf. And this example is like the example we had on our first page. So we're going to set it up the same way, conservation of momentum wise. So M1 V1 initial plus M2 V2 initial is going to be equal to M1 V1 final plus M2 V2 final. And so we also have conservation of energy. So energy initial is equal to energy final. So 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared is equal to 1/2 M1 V1 initial final squared plus 1/2 M2 V2 final squared. And so let's look at our equations and see what we have. So we have M1, we have M2, we have V1 initial, we have V2 initial. We don't have, as our unknowns, are V1 final and V2 final. So we have two equations and two unknowns. So we're going to have a system of equations. So now let's solve these simultaneous equations and let's plug in what we know first. So we know that the initial momentum is going to be 4.5 kilogram meters per second times 2.4 meters per second minus 2 kilograms times 4.4 meters per second. And so the reason this is a minus is because, like I said, momentum is a vector. And so the 4.4 meters per second for our V2 initial is in the negative x direction. So it's going to be a negative velocity, negative momentum. And so that's going to be equal to our final momentum. And that's equal to 2 kilogram meters per second if you plug in the numbers. And so let's do the same thing for our energy. So we calculate the energy of billet ball 1 and the energy of billet ball 2. we add them up together. That's going to be equal to our final energy. And if you plug those numbers in, you should get 32.32 joules. Okay, so now we have these two equations, and with the numbers plugged in, it looks a bit nicer. So in the second equation, we have squared, and of course the variables we are solving for are v1f and v2f. So the first equation looks nicer to solve for one in the other, because what we're eventually going to do is plug one equation into the other. So let's solve for v2f. If we solve for v2f, we will get rid of that term in the second equation. And because we're solving for the kinetic energy of billet ball 1, we're more interested in finding what v1f is equal to. It just saves us a bit of time. So that's going to be equal to 2 minus m1 v1f over m2, which is equal to 2 minus 4.5 v1f, if I just plug in the mass numbers, which I know, over 2, which is equal to 1 minus 2.25 v1f. So now we have our substitution that we can use to plug in to this equation. So let's do that. 1/2 m1 v1f squared plus 1/2 m2 1 minus 2.25 v1f all squared is equal to 32.32. And so now what we've got to do is plug in the mass numbers we know and multiply out this quadratic. So we'll make some room up here, but I'll keep the equations we know. So v2f is equal to that. We sub in. Okay, so now let's plug in the numbers we know and let's see what happens there. So 1/2 m1 is 1/2 4.5, which is 2.25 v1f squared, plus 1/2 m2, which is just 1, multiplied by 1 minus 2.25 v1f all squared, which is equal to 32.32. Okay, so now let's multiply out the quadratic. 2.25 v1f squared, the 1 in front of our bracket goes away because it's just 1. 1 multiplied by 1 is 1. Our second term is going to be negative 2.25 v1f minus another 2.25 v1f, and then 2.25 v1f squared is equal to 5.06 v1f squared, just the v1f squared, not the 5.06, and that's still equal to 32.32. Now, this equation looks like a quadratic. So, we should get it in the standard quadratic form, right? So, if we add up all the v1f squareds, we're going to get 7.31 v1f squared minus 4.5 v1f, if we add up all of the v1f terms, and if we subtract 32 from the other side, we're going to get negative 31.32 is equal to 0. And this is our quadratic equation. So now all we have to do is solve it. So v1f is our variable. So v1f is equal to negative b. So this is our b, this is our a, this is our c, if you remember the quadratic equation. 4.5 plus or minus the square root of 4.5 squared minus 4 times 7.31 times minus 31.32 all over 2 times 7.31. So I just plugged in our numbers for the quadratic equation. So let's simplify this. V1F is equal to 0.308 plus or minus the square root of 936 over 14.62. I already divided by the 2a on the bottom for this term over here. And so that gets us 0.308 plus or minus 2.093. And of course, you can always check on me if I've done my math right. Just plug it into your calculator and this should be okay. And so what two values do we get? We either get 2.401 or negative 1.785. Now, it can't be this number, can it? Because V1 initial is equal to 2.4. And so that number would mean we gain velocity from a ball crashing into another ball going in the opposite direction. So they come here and they crash. All of a sudden this ball has more velocity after it crashes. That doesn't make physical sense. So we know for a fact that that isn't the right answer. So it must recoil and have a negative velocity afterwards. So V1F is equal to negative 1.785.